Good morning. Well, first, welcome, of course, to the second day. This is not the welcome to the second day. We are about to set up we have succeeded to set up the online link. So I just got informed. I was just about to ask you for 5 more minutes because our online connection didn't work, but I just got the heads up from the back of the room. So then I hand over to... Okay. So now this is the welcome to the second day. So first of all, I hope you all enjoyed yesterday, the icebreaker. I think this was a wonderful occasion to connect, to discuss in a very relaxed way. I hope everybody had a chance to enjoy the ice creams, which came with very interesting flavors. So I had black white chocolate, which was an interesting experience. But then also I have seen that many of us have been taking the opportunity to walk through Tallinn, having a look at the city, having a look at the old city, and then slowly strolling in here. And I also realized that on the way through the center, we lost some colleagues here and there going to one of the nice restaurants on the parks, on the square. So for today, we're having again a bit more serious business. So after this very brief introduction, we will have the eco presentation. And then, of course, also, as we did yesterday, the Q&As, which we're following up in order to get the feedback from you, get the questions from you, and to see how far we get also here with collecting your input. Then we have a lunch break. We are aware that it's quite a stretch between now and lunch. But then you get served your lunch break at 12 o'clock. And then in the afternoon, we will have the last of the 4 missions. We will have the presentation and the Q&A for CryoRad. And then after a coffee break, there will be a general discussion again, so like we did as well yesterday, which can then be opened up to the 2 teams and also then, of course, to Isa and all of the members that are here in the room. And then we will close around 5 o'clock with basically closing, providing you some indication on the way forward, and also to summarizing the event that we had here. As I said, also giving you a bit of an outlook of what's going to happen after this meeting. As we have the stream running, I would suggest we are starting already with the eco presentation. And I invite Thomas Auguste to the podium.
Hello. Hello. All right. Good morning. What you are going to experience now is the result of a broad, collegial, multidisciplinary effort. My name is Thomas Auguste. I'm the Eco Mission Scientist at ESA. That should have been the slide when I say that. That's a broad, collegial, multidisciplinary effort. Our planet is sick. It has fever. We all experienced it in the past days. This year again, groundbreaking temperature records, droughts are raging, glacier and ice sheets are melting, sea level is rising, and many more manifestations of climate change. One parameter underpins this all, the Earth's energy imbalance, the difference between the incoming solar and outgoing terrestrial energy that the Earth traps. Of course, the root cause is identified: greenhouse gas emission and fossil energy. So humanity is taking actions, Earth's actions. If Paris Agreement was fully implemented in time, models predict that temperature would reach a maximum in 2070 and slowly recess. So if the surface parameter is your metrics to evaluate the effectiveness of the climate policies and their implementation, this is how long you'll have to wait. If you could observe the energy imbalance directly, you'd see it peaking around 2030, 4 decades earlier, providing the right, actionable feedback at policy timescales. The relationship between Sun-Earth energy balance and surface temperature has been long established. In 1822, Joseph Fourier described it in the Théorie de la chaleur, way before Maxwell equations got discovered. In 1896, Svante Arrhenius, Swedish Nobel laureate, quantified the global warming effect of CO2 emission from the Industrial Revolution that just started, thinking it was a blessing to get milder climate in Sweden. But the geoengineering idea is still very present today. States and private funds are looking into ways to make the planet brighter to restore the energy balance, while still emitting, while still drilling. In the absence of energy imbalance knowledge and of validated models, It's like prescribing paracetamol to a patient suffering severe fever, not treating the cause of an infection, not being quite sure of the dose to administer, and even worse, not having a thermometer to monitor the effect of the treatment. Because the big problem is, though this fundamental climate parameter was identified 200 years ago, there is still no observing system providing the energy imbalance with the required latency, accuracy, and independence to understand the radiative impact of human activities and of the Earth's mechanisms that have already been triggered. Ladies and gentlemen, introducing ECHO. I'm leaving you now in the expert hands of Benoît Messignac, specialist in Earth energy cycle.
Thank you, Thomas. As Thomas said, Earth is warming. It has been steadily warming for decades now, breaking regularly new records, and as it will probably break a new one at the end of this year. This alarming warming, unprecedented in past thousands of years, shows no sign of stopping. Actually, we are debating in the climate science community today whether it's set to further warming. So it's directly linked to anthropogenic greenhouse gas emissions. These emissions have increased the concentration of greenhouse gas in the atmosphere, disrupting the radiative balance at the top of the atmosphere between the incoming solar energy and the outgoing energy. And this generated an initial warming which triggered a number of feedbacks, of positive feedbacks, including water vapor, lapse rate feedback, the surface albedo feedback, and the cloud feedback, which further amplified the imbalance at the top of the atmosphere and the warming. And so we are now in a state where the energy budget of the Earth is imbalanced. The Earth receives 1 watt per square meters more of energy from the sun that it emits towards space, and it's storing this energy. Almost all this energy is entering the ocean because the ocean has a heat capacity that dwarfs that of the rest of the system. And the rest of the energy is warming land, ice, and atmosphere. That's the flow of this energy in the system and its storage that generate what people call climate disruptions. When the energy enters surface and the atmosphere, it raises surface temperature. When it enters the cryosphere, it melts ice, making sea level rise. When it enters the ocean, it expands seawater, making sea level rise. And when it flows in the atmosphere, it makes more frequent extreme weather, like heat waves becoming more common and hotter, more intense droughts, and heavier rainfall and flooding. So as you see, the energy imbalance is a fundamental physical variable that drives global warming and the associated climate disruptions. And as Thomas said, it's been 200 years, more than 200 years since Joseph Fourier that we've been knowing that anomalies in energy imbalance sustained over a while drive global warming and global cooling. So by that time, you would expect we would know what is the current energy imbalance, what was its past variations, and why it's changing. Well, the truth is we don't. Let me take you an example. We have several lines of evidence showing that energy imbalance has probably doubled between 2000 and nowadays, meaning climate system is probably warming twice as fast today than only in 2000, and we don't know why. None of our climate model simulations is reproducing this trend in Earth's energy imbalance. We have 3 options, 3 hypotheses. First, the energy imbalance record is wrong. The trend is too large. Fair enough. So that means we're not measuring energy imbalance properly. Second, we're wrong. Climate sensitivity is much larger than expected and much larger than in our climate models. Well, it means we cannot predict climate change in 2100. The other one, internal variability is much larger than expected. Okay, but that means we cannot predict the climate in the next 10 years. Either way, you see that we are in a profound ignorance in the fundamental variable, the most fundamental variable of the climate system, which is the energy imbalance. How come we are such a state? What are we missing? So the main problem is because the energy imbalance record is made of, it's a kind of patchwork of many measurements from different missions that has never been designed to detect this small 1 watt per square meters of imbalance hidden in the hundreds of watt per square meters entering the system and hundreds of watt per square meters leaving the system. We have the outgoing radiation measured by Ceres and its polar orbiters. We have the daily cycle of clouds and radiation, so important because it's aliasing for longer time scales, measured by geostationary satellites. And we have the solar radiometers on TESIS, on the ISS, like TESIS, for example, measuring the incoming solar irradiance. And brought together, all what they show, it's an accuracy of plus or minus 4 watt per square meters on the temporal mean of the energy imbalance. That's far too large if you want to detect and quantify the 1 watt per square meters of energy imbalance induced by greenhouse gases emissions. So what people have done today? Well, to address this problem, what they've done is to mix this data with other data of the ocean heat content, which is measured and estimated with satellite altimetry and the Argo network of profiling floats, and also space gravimetry. And so they got to an accuracy of 0.3 watt per square meters. But it brings in 2 new problems. First, you need 20 years of ocean heat content record if you want to have the trend right to get this level of accuracy. Means you have a 20-year latency on this accuracy. Second problem, now in the energy imbalance record, we are mixing information from the top of the atmosphere, top of the atmosphere radiation budget, and information from surface energy budget. And that's an issue if you want to attribute and explain global surface temperature, as I will explain afterwards. So we are today in this situation where none of the current or planned observing systems provide high accuracy, short latency energy imbalance measurements, which are independent from ocean heat uptake. We have designed ECHO to solve this problem. ECHO, the goal, is to provide energy imbalance with an accuracy of 0.3 watt per square meters on an annual basis. By doing that, we will address 9 key scientific questions about the energy cycle, which is the overarching theme ST3 in the ESA Science Strategic Plan, and will provide significant progress on 3 areas of action, A1, A2, and A3. These 9 science questions, or science objectives, as you wish, they are distributed into 3 science goals. The first is about present climate. We will be able, with ECHO, to understand ongoing climate trends and variability on energy imbalance and global surface temperature. The second one is about future climate. We will better constrain the warming projections and improve Earth system models. And the third one is about climate action. We will provide timely, objective evidence to steer climate action. Let's look at the first one, present-day climate. The first thing ECHO will provide is a measurement of the energy imbalance with a better accuracy. And this one will help us to constrain all the estimates of the different fluxes of the energy cycle. It's a long-standing objective of the World Climate Research Programme. The WCAP created in 1988 the GWEX core project, and the objective was to characterize those fluxes of the energy cycle. 40 years later, many satellites later, here is where we are. We've made great progress, but still, look at the uncertainty on these fluxes. It's a few watts per square meters. Several times the level we want to reach if we want to track this excess of 1 watt per square meters of energy in the system into these different fluxes. By getting to this level of accuracy with ECHO, we will reduce this to a few tenths of watt per square meters, sufficiently so we can track this excess of energy in the system. Even better, because ECHO will observe a current period, which is a warm period, we will be able to compare to a colder period earlier in the record. And we will be able to make the difference, to analyze the difference in the fluxes between this cold period and a warmer period. That will enable us to characterize how the fluxes are changing, not with time, with warming. Because when you do that with warming, you can characterize the climate feedbacks, and we will do that on the fluxes themselves. That's very promising. Now, ECHO is also about, in present climate, we want to explain the changes in global surface temperature. At internal time scale, the atmosphere is in equilibrium with the ocean mixed layer, meaning both are forming the same single system and their energy content is co-varying with time. You can see that in this Hofmüller diagram of the energy content in the atmosphere and the energy content in the ocean. It's taken from reanalysis. And you can see that the energy content in the ocean mix layer here is co-varying precisely with the atmospheric energy content. And both are making the same system characterized by one scala, which is the global surface temperature. A simple energy budget tells you, oh, it was. A simple, that's not the one I wanted. Anyway, a simple energy budget tells you that the anomalies in global surface temperature, they are driven by anomalies in the fluxes at the top of the atmosphere, which is at the EI, and the anomalies at the bottom of the ocean mix layer, which is the ocean heat uptake. And recent results show that anomalies of about 0.5 watt per square meters in isotherm here lead to anomalies up to 0.25 Kelvin during Nino events on the global surface temperature. And that's what drives the extreme in global surface temperature on annual time scale. And so with ECHO, by measuring this, the energy imbalance independently from ocean heat uptake, we will be able to determine what is causing those extremes in global surface temperature, especially during Nino years. It's not only about annual extremes, it's also about decadal variability. There are periods of slower and faster warming, periods of hiatus, like in between 1998 and 2012. And we know that a few watts per square meters sustained over a decade are sufficient to explain those periods. By observing a recent period with ECHO, comparing it with previous period in the record, we will be able to say whether today we are actually accelerating, if the warming is accelerating, and we will be able to know whether this is coming from the ocean or the top of the atmosphere. Now, ECHO is not only about present climate, it's also about future climate. Let's now look at the energy budget, and let's now decompose it in terms of radiative forcing and radiative response of the Earth. At the first order, the relative response of the Earth is linear with surface temperature, which means that when you have increased greenhouse gas concentration in the atmosphere, like in this simulation, you expect surface temperature to increase, and you expect the energy imbalance to decrease and decline towards zero. The slope of this line is the global climate feedback parameter. The temperature you get when the energy imbalance finally gets to zero is a climate sensitivity. It tells you how much warming you can expect given a certain amount of greenhouse gas in the atmosphere. It's a fundamental metric because it's the only one we have to constrain our climate projections. And it has been repeatedly used in IPCC reports to reduce the uncertainty in their projections of future warming. Now, the only way we have to estimate the climate sensitivity in the real world is to measure surface temperature along with Earth's energy imbalance and to regress one over the other. By increasing the accuracy on the Earth's energy imbalance, ECHO will enable to decrease the uncertainty on the estimate of the climate sensitivity and strengthen our observational constraint on the projections of future warming. Now, let's look a bit more into the details. The problem is that when you look into the details, climate sensitivity and the global climate feedback parameter are not constant with time. They are changing slightly with time. And these changes, it's because the climate feedbacks are sensitive to the surface pattern, to the pattern of surface warming, especially in the tropic. Because this pattern of surface warming is changing with time, the global climate feedback parameter and the climate sensitivity is changing with time, meaning there are periods where we are less sensitive and there are less warming for the same amount of greenhouse gas concentration in the atmosphere, and periods where we are more sensitive and there is more warming. And we want to understand these periods, to understand this, to be able to explain why we have more or less warming, and it also gives us a more stringent constraint on the climate sensitivity. To do that, it requires you have Earth's energy imbalance measurements independent from the ocean heat uptake, because the ocean heat uptake is the main driver of the pattern in sea surface warming. That's what ECHO is designed for. Now, ECHO will also help us to improve Earth system models. So the Earth system models is a central tool in climate science, but more than that, it's probably the unique tool we have to estimate or to project future warming at regional and local scale. And so it's also our unique tool to assess potential future impacts, because impacts are at local scale. But the problem is that the Earth system models still show large biases in outgoing shortwave and long-wave radiation, which prevents from predicting energy imbalance trends and variations. And ECHO, by providing unprecedented accuracy on a seasonal basis of the relative budget over the whole Earth, it will provide the fiduciary reference data with which we will be able to assess climate models. And even better, to detect deficiencies during the development of these models and to guide improvement. Now, ECHO is not only about climate science. ECHO is also about societal benefit and for humanity as a whole. You all know that in 2021, sorry, no, it's not in 2021, it was earlier, during the COP21 in Paris, all nations of the world have committed to reduce their greenhouse gas emissions in order to keep the warming well below 2 degrees. That means that in the coming decades, we expect to see fossil fuel emissions to phase out. We expect to see them phasing out. And we know that the first variable that will react to that will be the energy imbalance. It will peak and decline decades before surface temperature stabilize. With ECHO, we will be able to detect this peak and quantify it, meaning that decades before surface temperature stabilize, we will be able to evaluate the efficiency of our mitigation policies, but also we will be able to know if it's sufficient to stabilize below 2 degrees as we committed to. So it will provide timely evidence to steer climate action. Now, imagine that in the course of the 21st century, while we are reducing our greenhouse gas emissions, it is decided to deploy, whether in a concerted effort or in a rogue unilateral action, to deploy some techniques to cool the Earth, like with climate intervention. ECHO will be our unique capacity, if we make it fly, to know what is the effective radiative effect of these climate interventions. So that would give objective evidence to monitor and to govern what would be an unprecedented and potentially very dangerous interference with our climate system. Now, with that, I leave you in the hand of Jackie Russell. She's an expert on radiation measurement by satellite.
Benoit has told us about the goals that we have, our science goals. I'm going to tell you the requirements we have for ECHO to ensure that we can meet them. Our first objective is to measure the Earth energy imbalance on annual timescales with very high accuracy and stability. This is a matter of resolving a very small residual between large incoming and outgoing terms. This about 1 watt per square meter, that means that we are not having this nice balanced picture that I'm showing here. Our second objective is to provide global maps of the reflected shortwave and emitted longwave fluxes anchored to the Earth energy imbalance, sufficient to enable their interpretation. We've been putting radiation budget measurements on satellites since 1959, when Explorer 7 launched carrying SUMI's radiation and heat balance detector. Since then, there have been numerous missions dedicated to measuring the global radiation budget or focused on processes, but none of these have sufficient accuracy to provide an independent measure of the Earth energy imbalance of our planet. This is because all the current radiation budget missions are designed to measure mapped fluxes, not Earth energy imbalance directly. We've already heard that the best satellite observations of the radiation budget rely on multiple external sources of information and are subject to their errors. We can correct orbital sampling biases in the Earth energy imbalance derived from series shortwave and longwave fluxes using geostationary images. But we need to make a much larger correction of 3 watts per square meter to those fluxes in the most plausible way to make the result consistent with the Earth energy imbalance derived from our best estimates, primarily based on ocean heat content anomaly data. ECHO needs to do things differently, directly measure the energy imbalance to provide an independent observation. It needs to measure all the components of the energy imbalance in a self-contained and consistent way. It needs to address the issues causing this error to achieve an order of magnitude improvement in accuracy, address the calibration and intercalibration issues, address the uncertainties associated with the angular and temporal sampling problem of the outgoing fluxes. To solve the angular sampling problem, ECHO will use a wide field of view absolute radiometer to directly measure the true outgoing flux, both the reflected shortwave and the emitted longwave at satellite altitude. The field of view will capture all the rays exiting the Earth, visible from the satellite altitude, and exiting the atmosphere system from a defined reference surface up to 100 kilometres at the limb, capturing the radiative relevant part of the atmosphere. It will also directly measure the twilight flux when it's in the field of view by measuring the reduction in the direct solar beam transited through the atmosphere along the terminator. To solve the calibration and intercalibration problem, ECHO will provide a self-contained, intercalibrated measurements of all the components of the energy imbalance, with absolute radiometers measuring the combined shortwave and longwave components of the total outgoing with the Earth viewing radiometer and the incoming with an absolute solar radiometer on the same platform with common metrology. The ability to cross-check calibration between the incoming and outgoing radiometers will be enabled by occasional sun-pointing of that Earth viewing radiometer. ECHO's observation of the Earth energy imbalance in concept is a calorimeter experiment on the Earth, measuring the energy in and out through the control surface. Given the temporal and spatial variability of the outgoing energy, sampling is the last issue we need to solve. You can't cover the whole reference surface with observations all the time. To solve the spatial and temporal sampling problem, the ECHO mission requires a constellation of wide field of view radiometers on processing satellites sufficient to provide statistically representative sampling of the diurnal cycle on annual to sub-seasonal timescales. We can do this with a constellation of 2 processing satellites in 82-degree orthogonal orbits. In essence, the constellation is the instrument, along with the wide field of view for the direct flux sampling and intercalibrated absolute radiometers to measure both the total outgoing and incoming radiances. ECHO provides a novel solution addressing the calibration, intercalibration, angular and temporal sampling uncertainties to realise the 200-year-old aspiration of directly measuring the Earth energy imbalance. As well as measuring that global imbalance, we also need to provide maps of the reflected shortwave and emitted longwave fluxes anchored to the measured imbalance to help us interpret it. The total outgoing measurements made with the wide field of view radiometer are essentially a very high absolute accuracy but for very low spatial resolution observation of all the outgoing energy, covering the reflected and emitted spectral ranges. We need to resolve this into the constituent reflected shortwave and emitted longwave components at a spatial resolution of 10 to 50 kilometres on monthly to seasonal timescales. The flux maps need to be anchored to the high absolute accuracy of the energy imbalance observation to underpin their calibration. ECHO will use images covering the wide field of view to provide the spatial and spectral information we need to resolve the flux maps. Because these images match the field of view of the high accuracy total outgoing measurement, we can achieve intercalibration by integrating quantities over the footprint to anchor the products to the Earth energy imbalance. This can be done at very high cadence throughout the satellite orbit. The higher spatial resolution image observations don't directly sample the flux, so they must infer it from the observed radiance. So we need to account for the variation in the observed radiance with viewing geometry. In the long wave, this variation occurs with viewing zenith, referred to as limb darkening. In the short wave, it can be described by angular models of the anisotropy factor. These characterize the proportionality between the radiance and the flux as a function of viewing zenith and relative azimuth between the view angle and the sun for a given scene and solar illumination. ECHO's derivation of mapped fluxes will take a very long-established approach of employing observationally derived, scene-dependent angular models like the one shown here. But it will employ greatly improved angular sampling of the observations to improve the result. The high cadence and wide angular range of the imager observations will provide multi-angle measurements of every scene over a period of minutes as the satellite orbits. This will enable observationally based angular models to be built up much more quickly than is usually the case, and offer opportunities to update them regularly if we wish. It will also reduce the noise on the flux derived using these models by offering multiple opportunities for conversion from radiance to flux, reducing observation angle-specific bias. And we can avoid unfavourable observation angles for particular scenes where radiance to flux conversion is very prone to error, such as ocean glint. These images are multispectral images. They have spectral channels across the short and long-wave spectral regions, chosen to enable a good narrowband to broadband conversion, which we need to resolve the total outgoing measurement, and to facilitate scene identification, which we need to build up and apply the angular models for radiance to flux conversion. The spatial resolution of the images is what we use to resolve our low-resolution measurement into our mapped fluxes. But they're actually driven by the scene ID. And they need to be met not just over at nadir, but over the whole central portion of the wide field of view, which is the portion that is sufficient to span the equator without gaps in a day, where we resolve the 10 to 50 kilometre resolution mapped fluxes. So, ECHO is a novel solution to a 200-year-old problem, namely a sufficiently accurate, direct and independent determination of the Earth energy imbalance. It will also provide maps of the reflected shortwave and emitted longwave components of the radiation budget, sufficient to enable interpretation of that balance. We've designed it to address the issues of measuring the imbalance. It is a self-contained mission, measuring all the components, directly sampling the outgoing flux, and employing a constellation of precessing orbits to ensure sufficient diurnal and seasonal sampling. It's complemented by multispectral, multi-angular images which resolve the wide field of view that can be intercalibrated, that provide the map fluxes that can be intercalibrated to anchor the product to the Earth energy imbalance that we measure. And now I would like to hand over to Anna Lequillot, ECHO's study manager, to take us through the technical details.
Thank you, Jackie. So the ESA team is now going to present the two technical concepts of the mission. And these were derived by two industrial teams. OHB for concept A, I think Javier is here. Yeah, and Thales Alenia Space for concept B. I think the colleagues are here. Yes, thank you. And also the ECO end-to-end simulator whose team is not here today. So we start with our observation concepts, and I will explain the driving requirements, and then my colleagues will go from that and define or detail the actual technical spacecraft and payload concept. So obviously here we start with what we measure, the whole Earth and then the Sun. And from that, the first set of driving requirements, as explained by Jackie, is the need for the constellation, the mission requirements. So we need to sample the diurnal cycle. We need to sample the Sun twice per day, and we need to maintain the control surface, the little blue surface, accurate to plus minus 1 kilometer. Then the second set of driving requirements is the first set of mission objectives, measuring the EI. So we measure the Earth with the wide field of view radiometer and the Sun with another Sun radiometer. They have some accuracy requirement, but the really crucial one is the differential bias, because that's directly linked to the EEI error budget, as Thorsten will show, which needs to be extremely accurate between 0.3 to about 0.3 watts per meter square. Finally, the second set of mission objectives means we need to have cameras looking at the same area as the radiometer. And there's a number of channels. And of course, we have performance requirements on these cameras. So here the total requirements, I might not go through them all, but we have the diurnal cycle sampling and the control surface. And Andrea and Luca will report on this. the ISR accuracy and the differential bias that I mentioned. And for the imagers, we have a spatial resolution that must be between 2 and 10 kilometers for linear and SWIR. 1.5 for visible, 2 to 10. I'm very sorry, 1 to 5 kilometers for the visible and 2 to 10 kilometers for the SWIR and the thermal infrared. And SNRs at about 100 to 1 for visible, and the equivalent NEDT, noise equivalent temperature in tier of between 0.4 and 0.7 kelvins. And the channels, I'm not going in detail, but we have red, green, blue. We have one whole channel for the SWIR, and we have 6 channels for the tier, as Jackie mentioned, ranging from 6 to 14 micrometers. That's the requirement. Now my colleague Andrea Malgarini, the system engineer, will take over.
Thank you, Arnaud. The diurnal cycle sampling is one of the key requirements for the ECO mission, and this can be directly addressed, as mentioned before, by the orbit selection. Precessing orbit were mentioned, and in particular, the point of interest is indeed the precession rate of the orbit with respect to the Sun. This item can be controlled by 2 important orbit elements, which are the inclination and the orbit altitude. And as you can see here, by varying the inclination, we can tailor how many diurnal cycle we scan over a year. Going to lower inclination allows more diurnal cycles at the cost of losing coverage of the whole Earth. For ECO, a solution was found in orbits around 82 degrees, where we have an integer number of cycles of 4 over a year, that you can see displayed in the picture. And to go above this number, the solution is to introduce a second satellite which effectively covers the gap with respect to the plot I was showing before in an orthogonal orbit. With this, we are able to cover 8 diurnal cycles in 1 year with the whole constellation. One final note on the orbit is on the eccentricity selection. We go for a frozen orbit, which means that the eccentricity is numerically computed to balance out the gravitational perturbation on the argument of perigee and eccentricity. And this will provide an inherent robustness on the control surface, for which we require 1 kilometer stability. So the next point is on the constellation deployment. We start with a baseline Vega C launch. And the first challenge is how to fit the 2 satellites. So to do so, we stack them together. Both industrial consortium came to the conclusion of 2 cubic-shaped satellites to be stacked on top of each other. And the next point is how do we get them with a single launch to orthogonal orbits. The way to do so is to use the same concept I just discussed, the precession. So we place the 2 satellites in 2 orbits which are just a bit offset with respect to the nominal one we just presented, so that the precession rate for the 2 orbits will be slightly different. And over time, it will cause the satellites to drift apart. When we reach the 90-degree separation for the orthogonal orbits, the 2 satellites will thrust back to the operational orbit to start operation. This whole phase will last 1 year. And after that, operations will start with the diurnal cycle sampling and the Sun observations, concluding with disposal with a controlled re-entry. Regarding the operations, these address directly the observation requirements. The first part is to have nadir sampling of the total outgoing radiation with the radiometer, which is shown here in white. With collocated set of imagers for the shortwave and the long-wave radiation. And they provide special context to the radiometer information at a sampling of 30 seconds. The second point, as mentioned in the requirements, is the need to do sun observations. And to do so, we have a dedicated sun radiometer, which we will point at the sun twice a day by pitching the satellite. And last, one comment on system aspects, because the precessing orbit has the advantage of providing us a a good ground for observing the diurnal cycles, but in terms of system, they present some challenges, since if we fly in a fixed configuration, the satellite will see the sun coming from all the angles throughout the season, which will make power generation and thermal stability challenging. Both consortium came to the conclusion of implementing a slow rotation around the zenith angle with a rotating solar panel, so that the satellite can control the azimuth position of the sun with respect to the satellite, and the solar panels can control the elevation, so that we have maximum power generation in this sense at a smaller size solar panel. And at the same time, we keep 3 faces pointing at deep space for thermal stability reasons. On the system note, now we go to the 2 concepts, one after the other. So the first one is here, as I briefly spoiled before. It comes in a cubic form with a face dedicated to the Earth instruments with the Earth radiometer and the TIR VSWIR cameras. And then we have one orthogonal face containing the sun radiometer, which is the one we use to pitch at the sun. We have one single wing, which will be used to track the sun and generate power. All the avionics components are based on Copernicus heritage. You can see here the budgets, with the important note that delta V here is sized for controlled re-entry. The second concept comes also very similar, so independently the 2 consortium reached the same conclusion. Single solar wing, cubic form factor, with one face for the Earth radiometer and the cameras, and in this case one opposite face for the sun radiometer, which will be pointed at the sun. Also in this case, avionics is based on Copernicus heritage, and the delta V is compatible for controlled re-entry. One final slide for the launcher compatibility. We mentioned before, Vega C is the baseline. The 2 satellites are stacked on top of each other. And in both cases, both volume and mass-wise, they fit in the launcher. As you can see here, the breakdown, the payload mass is around 110 kilos for both. And on this note, I will leave the floor to Luca Schifano, payload manager for the ECO mission. We will talk about the payload architecture and performances.
Thank you, Andrea. So the payload of ECO consists of many instruments, but all of them work together to provide for the different components of the Earth's radiation budget and the Earth's energy imbalance. First, the Earth radiometer measures the Earth's total outgoing radiation. This instrument is at the core of the ECO payload and works in synergy with all the other instruments. Second, we have a solar radiometer that measures the incoming solar radiation, and together they will provide, with a differential measurement, the Earth's energy imbalance, which is the mission objective 1. But at this point, we only have the radiometric information. So these radiometers are complemented by a suite of multispectral imagers covering the visible, shortwave infrared, and thermal infrared domains. When you combine the information of the imagers with the Earth radiometer, you obtain the reflected shortwave radiation at high resolution. And when you do the same for the TIR cameras with the Earth radiometer, then you obtain at high resolution the emitted long-wave radiation. Together, they map the Earth's radiation budget, which is our mission objective 2. Let me now go through the key requirements and drivers for the radiometers first. So here, the radiometric accuracies are very important, as you have understood from the science presentation. This will drive the electronics of both radiometers and the thermal behavior that will be specific to each of them. The acquisition mode, you will see, will differ for each radiometer. The acquisition mode is also driven by spatial requirements, because the field of view will be very different for the Sun and for the Earth. Also, that field of view will drive the radiometer cavity geometry. And for the spectral requirements, we will need to measure the incoming solar radiation and total Earth outgoing radiation from 0.2 to 100 micrometers, which is a very wide spectral range. This will drive the radiometer coating efficiency. So let me start with the solar radiometer, which points towards the Sun to measure the total solar irradiance, or TSI. This type of measurement has a long space heritage, with TSI measurements performed from space since 1979. The key point here is the measurement principle, the electrical substitution principle. When the shutter is open, solar radiation enters the cavity, which is coated with a highly absorbent black coating, and that absorbs all the radiation from ultraviolet to far infrared. This heats the cavity. When the shutter is closed, no radiation enters the cavity anymore, and we are putting an electrical heater to reproduce the same thermal state as when the cavity was open. So in a sense, when measuring the sunlight, we are not measuring the sunlight directly, we are measuring the electrical power that is needed to reproduce the same thermal state. And because we know a power and we know exactly with the precision aperture that you can see here on the left, this is really precise, such that we can measure the area from which the total amount of radiation is passing through, so we are measuring in watt per meter squared. We are basing this on 3 cavities. Here you see 2 cavities. The first one is the scientific for scientific measurement. We have a second cavity that is the reference one that allows for internal comparison. And we're also adding a third cavity for redundancy and stability monitoring, specifically also for the coating to measure the aging. Now moving to the acquisition concept, which is called the shutter operation. The use of shutters allows the instrument to alternate between illuminated and non-illuminated states. And this is essential for the electrical substitution principle, because the instrument needs to compare the thermal effects from the sun with the thermal effect of the electrical input. So the shutter is sequentially open and closed, such that we nullify the temperature difference between the optical power from the sun and the electrical power from the cavity heater. That shutter operation also helps to separate between the useful signal from internal offsets and thermal background effects. So our proposed designs for ECO builds on their heritage with 3 cavities and 3 shutters, as you can see on the right. For ECO, minimal adaptations are expected on the cavity and on the coating to replace the previous conical cavity coated with Actar black by a more performant flat cavity coated with Vanta black, which has been demonstrated in space a few years ago. Let me now move to the Earth radiometer. At first sight, it looks very similar to the solar radiometer. Again, we have the 3 cavities and 3 shutters. But the measurement problem is very different. You see, the solar radiometer measures the sun in a very narrow field of view, while the Earth radiometer will need to observe the Earth from limb to limb, including a 100-kilometer layer of atmosphere. This drives a much wider field of view, so we cannot use the same design as DARA. So we need a wide field of view cavity, as you can see here, and that will drive, instead of a conical cavity, we have an elliptical cavity. In addition, this drives a much bigger cavity than the solar radiometer, with a mass that is about 10 times larger. This larger volume has an important consequence. The thermal inertia is higher. The cavities and surrounding structure do not heat up or cool down as quickly as with the solar radiometer. So thermal stability becomes a central part of the measurement concept. To this end, the positions of thermal sensors and electrical heaters have been optimized to control the cavity temperature. This is directly linked to the radiometric accuracy. However, I say that we are about a volume that is 10 times larger than the one of DARA, but keep in mind that this is still a very small instrument. As you can see here, that same top part of the cavity that is about 3 to 4 centimeters. But the cavity is only a part of the radiometer. This cavity is put into a stable thermal environment, and in front of that cavity, we are placing baffles and shutters that define the field of view and also protect for stray light and thermal fluctuations. Here are a bottom view of the same radiometer. You can see that cavity is here. We have the 3 cavities. They are all linked by a common heatsink. So both radiometers are connected by a common instrument control unit. So we have seen the main components of the Earth radiometer composed of 3 wide field of view cavities. And I also mentioned that the coating for these cavities, coating inside the cavity, is the black velvet. So this black coating absorbs all the radiation from UV to far infrared. The other major difference with the solar radiometer is the acquisition mode. So the solar radiometer can use a shorter operation because the sun is stable on the relevant time scale. But the Earth radiometer cannot be observed in the same way because the Earth scene is changing continuously. Clouds, lands, oceans, and snow, you see they are all passing through the field of view. So because of that, we have developed through successful risk retirement activity, a new continuous acquisition mode that follows the Earth changing scene, but also the solar intrusion, because since we have a very wide field of view, at some time the sun will enter the edge of the field of view in the layer of atmosphere. So we are building on the last year's developments for the Choose mission, that a mission concept that was studied at ESA, and we are reusing that continuous acquisition mode for ECO. And this is not only theoretical, because we, through that risk retirement activity, we already reached the breadboard, and we intend to go even further in phase A should ECO be selected. So this slide summarizes the radiometer performance. As you can see, we have the requirements have to be less than 1 watt per square meters for the incoming solar radiation and for the total outgoing radiation. We are well below for both radiometers, 0.15 and 0.37 respectively for solar radiometer and Earth radiometer. But the most important thing, as you have seen before, is the differential error for the Earth energy imbalance, so differential error between these two radiometers that should be below 0.3 watt per square meters. This is very challenging, but we managed to obtain a value of 0.18 after several risk retirement activities, including one targeting the optoelectrical inequivalence that was the largest error source in the error budget. I also show for information the long-term stability. We are also well below the threshold for these requirements. Let me now move to mission objective 2. Here, the objective is to retrieve the Earth radiation budget into its reflected shortwave and emitted long-wave components. And this is done with the visible and shortwave imagers for the shortwave and the 6 thermal infrared cameras for the long-wave. So, let me come back to the same slide, but this time for the cameras. The spectral requirements will drive the number of spectral bands, because we cannot measure from 0.2 to 100 micrometers with the imagers, so we need to select a few spectral bands to retrieve from narrowband to broadband measurements. So this will drive the number of spectral bands, but also the number of cameras. Then the spatial requirements will drive the field of view, which has to be the same as the one for the Earth radiometer, and the image quality and complexity of these cameras. Therefore, also the choice of detectors will be driven by these spatial requirements. And finally, for the radiometric requirements, they will drive the SNR, NEDT, and ARA, as well as the acquisition mode if we use frame staking or time delay integration techniques. So a field of view of 130 to 140 degrees is very wide for an imaging system. Near the center of the field, maintaining image quality at and high SNR is manageable. The difficult region is at the edge of the field of view, as you can see here. With high field angles, the distortion increases, which degrades the spatial resolution, and also less signal is coming, so the SNR and EDT are also degrading. So this is where the challenges are. Let me now move to the Concept A cameras. We have 11 cameras, one for each covering one of the 10 spectral bands, with a 2-sphere camera to cover the field of view. So we are in total, so we have these 11 cameras. We have 3 visible imagers that are, the 3 are the same, except that one is for the red, another one for the green, and the last one for the blue. So all of them use the Pixelis 46 megapixel silicon detector with calibration density in the pupil plane. For the sphere, this is a similar design, but we are using another detector from NIT, an in-gas detector from that one to cover for the sphere. And the field of view is split in two to meet the spatial requirements. Finally, we have, so you see here in the bottom a view of these 3 visible and 2 SWIR cameras. And finally, for the 6 tier cameras, to cover the 6 narrow spectral bands in the thermal infrared, we also have a calibration shutter that is located near the detector. For the VIS, SWIR, and TIR camera designed for concept B, we only have 8 cameras. We have only 1 VIS camera that is making use of a biofilter for the Caspex 12 megapixels. The biofilter allows to measure the red, green, and blue at the same time, so only 1 camera for that. And we have a solar diffuser in pupil plane. For the SWIR camera, the optical design is very similar to the visible one. We are using another Caspex detector, the 1.3 megapixel, less pixels but with a larger pixel size, which will drive a lower spatial resolution but a higher signal-to-noise ratio. Again, we have a solar diffuser in the pupil plane. And for the 6 thermal infrared cameras, again, we use the same Pico 1024 microbolometer detector from Linred. The major difference with concept A is that the calibration shutter is located in front of the first lens instead of near the detector. So for a risk retirement activity, these cameras were optimized in terms of volume and mass, especially for the TIR cameras, as you can see, weighing less than 2 kilograms. I must say that here we have made tolerance analysis and preliminary stray light analysis. This is leading to compact but also very robust optomechanical designs. Now moving to the camera's performance, starting with the spatial resolution. For the visible, we need to be lower than 5 kilometers. Concept A is fully compliant over the field of view. You can see the curve, as I mentioned before. This is really on the edge of the field of view that it becomes more difficult. For concept B, this is the nominal design while it was compliant on the full field of view. After tolerancing, we see a marginal non-compliance at the edge of the field of view, but it does not affect the scientific product at level 2. For the SWIR camera, both concepts are compliant for the 10-kilometer spatial resolution. And for the SWIR camera, with the 6 bands, concept A is compliant over the full field of view. For the TIR camera, again, after tolerancing, we have a marginal non-compliance near the edge of the field of view, and again, it does not affect the L2 scientific product. Now moving to the radiometric performances, signal-to-noise ratio for visible and SWIR, and NDT for TIR. So concept A is compliant as well as concept B on the full field of view. Same for the SWIR, we are still compliant over the full field of view. For the thermal infrared cameras, concept A is compliant with margin at 0.4 Kelvin for all the thermal infrared channels, while for the concept B, so you can see here for the band 1, we are still below the goal and the threshold, between 0.4 and 0.7. For the other bands, we are even better than the goal, except a small non-compliance at the very edge of the field of view for band 5 for the cloud optical depth, where we obtained 0.45 Kelvin instead of 0.4 Kelvin at that edge of the field of view. Again, this does not affect the L2 scientific product. Now let's summarize the performance. ECO meets the mission requirements with double the minimum diurnal cycle sampling and with a control surface stability of less than 1 kilometer. This was presented by Andrea earlier. For the radiometers, we have seen the values we were with margin. We are compliant for the most important requirements. So finally, for the cameras, we have seen marginal non-compliance for concept B in the visible TIR, and for the band 5 NEDT for the TIR at the very edge of the field of view, but they do not affect the L2 scientific product, and concept A is compliant with all the requirements. So this is why I'm confident to tell you that for mission objective 1, we can meet it with the radiometer, as well as for mission objective 2. In summary, no technical showstopper has been identified on the key performance, and ECO has a solid technical foundation for continuation in phase A. I am now handing over Torsten Moritzen, expert in the Earth energy budget.
Thank you, Luca. So in this block, we will talk about the data products and the usage, and we will show you a little glimpse of all the research we have done to demonstrate the feasibility of ECHO. So this is an overview of the data products that we have, and don't worry, I will not go into details. The main takeaway from this is that we have 3 different types of instruments that work in synergy to obtain the 2 mission objectives, measuring the Earth's energy imbalance and mapping out the Earth's radiation budget. During phase 0, we have identified a large number of users of such data. This includes climate scientists, such as me, who will make direct use of the data. But there's also a number of other users, such as policymakers, that will be able to take advantage of the kind of high-level information that ECHO can provide. The interest in ECHO has actually been very overwhelming. As climate scientists, we are used to knowing that this is the most fundamental variables that we are looking at here, but this idea that the imbalance of the climate system is important has really spread to wide parts of society. During phase 0, we have conducted science studies. So this included setting up scenery for the types of instruments that we have. They are based primarily on observational products that exist, but we have also done simulated scenery to take advantage of the multi-viewing capability of the mission, which no other mission has, and also to study the narrowband to broadband conversion with a spectral view. This research has developed our forward modeling capabilities, and we are now at SIL4. But also beyond that, we have been moving towards SIL5 by building up the processing chains. We have estimated or evaluated some of the overall mission performance directly on the products, and we have conducted a campaign to verify the idea that we can cross-calibrate the cameras using the high-accuracy radiometers. Moving on to mission objective 1, the Earth's energy imbalance, I remind you, as you have heard several times, ECHO has a goal to measure Earth's energy imbalance with an accuracy of only 0.3 watts per meter squared and a threshold of 0.7. Reaching each of these levels will unlock new scientific capabilities. These are not just numbers. But it's a really daunting challenge. As I illustrate here in the bottom, this is the incoming radiation and the outgoing radiation, and we are looking for that small difference there. ECHO will observe the Earth's energy imbalance using wide field of view radiometers, as you have heard. They will measure the outgoing flux directly in space. This flux is then projected onto the control surface at approximately 100 kilometer altitude. And then also we measure the incoming solar radiation that is also projected on that control surface. And by keeping track of the incoming and outgoing radiation on that surface outside the Earth system, we can observe the imbalance. A special case happens when the twilight beam enters the radiometer. These are important. We want to measure them. So I will show you some of that research. During the phase 0, we have identified 4 general sources of errors: sampling the sun, sampling the Earth, the radiometric relative accuracy that Luca just showed you, and the issues with the twilight solar beam and maintaining an accurate control surface. In the following, I will focus on research looking at the Earth sampling and the twilight beam. Sampling the Earth's outgoing radiation is challenging because it varies by a lot. Okay? During the diurnal cycle, it changes from negative during night to positive during day by several hundreds of watts per meter squared. And not only that, it's also varying over the year. As you can see here in the bottom, in the northern hemisphere, winter, we have a surplus of about 10 watts per meter squared, and during summer, we are losing a similar amount. And not only that, the outgoing radiation, especially the solar reflected sunlight, can be very anisotropic, as you can see in this example, this extraordinary example of a sun glint in the image there. So this means that we need to sample the diurnal cycle, the annual cycle, and the full angular space. To study this problem, we have developed the ECHO mission performance simulator. This simulator simulates physical orbits of the constellation, calculates the flux that would be observed every minute during those orbits, and this data is then binned and averaged to yield the global annual mean Earth's energy imbalance. It turns out that the choice of orbit is decisive for ECHO's success. So in this animation, you see the very familiar sun-synchronous orbit. In this orbit, you observe basically 2 times per day. In this case, 1 o'clock in the afternoon and 1 o'clock at night. Now, imagine you should reconstruct the full diurnal cycle from these 2 values. You can't. So you need auxiliary observations, or you need a model to do this, or you need 6 to 12 such satellites. Another way to look at the problem is to plot the anomalies of the diurnal cycle as a function of the local mean solar time and the time of the year. You can recognize patterns such as the Northern Hemisphere winter maximum there, and the summer minimum there, most pronounced during midday. By taking the example of the sun-synchronous orbit, you can see that you will just be observing these 2 lines of data. It's very difficult to obtain the annual mean from this. But if instead we use 2 precessing satellites at 82 degrees inclination, we obtain a much better situation. You can see here in the plot to the right that 1 satellite in orange here and 1 satellite in gray will effectively observe the full diurnal cycle over the year. And as it turns out, also the full angular space. Consequently, we obtain an excellent sampling performance with this constellation, as you can see here in this summarizing table. With 2 satellites at 82 degree inclination, we obtain a sampling error of only 0.09 watts per meter squared on the global annual mean. But not only that, with a single satellite, as you can see here in the map, and also in the zonal mean plot, we can have compensating continental scale errors of up to 4 watts per meter squared. But with 2 satellites, seen in the lower map and in orange here, this is a much smaller problem. Moving on to the twilight beam. The sampling of twilight situations is an important part of the budget in the imbalance. So on average, 11 watts per meter squared averaged over the Earth's surface enters the control surface outside the Earth. And 1.5 watts less is going out to the satellite. So this difference must be accounted for. To this end, we have conducted detailed simulations of what these situations would look like. So here I'm showing you a plot of what the sun will look like from the view of ECHO. In this plot, we show what would be measured by the radiometers during a twilight situation. So on the x-axis, you have the angle to the sun, or equivalently the height above the horizon here to 100 kilometers. And in the red dash curve, you are seeing the incoming sunlight, taking into account the size of the sun. And in a solid line, you see the transmitted. And the difference between these 2 lines is that which is being absorbed and scattered by the atmosphere on the way through. So from this research, we have learned that we can sample these situations with the ECHO constellations with an error of less than 0.1 watt per meter squared with these 2 satellites. The accuracy of the control surface must be better than 1 kilometer. So that determines this cutoff here. And we can model these situations, but we really prefer to measure them. And there's good news that it can be done. And hopefully during phase A, we will also have an estimate of the measurement error during these situations. So here's a summary of the error budget for the Earth's energy imbalance. You can see that across the board, ECHO is very close to achieving goal performance, which again, I'll just remind you, is an order of magnitude better than the state of the art. The relative radiometric accuracy that Lucas showed you, if you paid attention, he had a smaller number. This is now projected onto the surface of the Earth. So in total, we are very, very close to reaching goal performance here. So this level of performance will allow us, for the first time in 200 years, to verify the theory of climate that Fourier proposed. So next, I will hand over to Steven de Witt, who is an expert in radiative flux missions.
As already introduced before, ECHO is designed from the start to measure accurately the Earth energy imbalance, but also to measure both accurately and with high spatial resolution the underlying fluxes of Earth radiation budget. And for this, we rely on 2 instruments. For the accuracy, we rely on the wide field of view radiometer. The wide field of view radiometer is an absolute instrument which measures the true flux at satellite altitude. The field of view of the wide field of view radiometer on Earth is a circle with a diameter of 6,000 kilometers, which means that the radiometer measurements are quite low in resolution. And therefore, we complement the radiometer by cameras, which provide both high spatial resolution and also spectral detail. The basic measurements of the radiometer, of the cameras, are level 1 radiances at the top of the atmosphere. To convert those level 1 radiances into the primary level 2 product, which are broadband fluxes, we need to overcome 2 challenges. The first challenge is the challenge of angular sampling. So we need to convert the radiance to flux. The second challenge is the challenge of spectral sampling. The cameras measure in relatively narrow spectral bands. And so we have to convert the spectral information to broadband information. That's the spectral sampling. Another very important key aspect of ECHO is the cross-calibration of the cameras by the radiometer, where we transfer the accuracy from the radiometer towards the cameras. And this cross-calibration becomes possible because the entire field of view of the wide field of view flux measurement is covered by spatially resolved radiances measured by the cameras. For the long-wave spectral problem, we have 6 spectral channels measuring the main greenhouse gas absorptions by water vapor, CO2, and ozone, as well as the cloud optical properties of cloud temperature, cloud optical depth, and cloud phase. From the measured spectral information, we reconstruct by regression the broadband flux, and this regression is trained on a well-established database of simulated scenes. And from the simulation, we estimate that at the monthly mean level, we can reconstruct the broadband flux with a fidelity of 0.7 watts per square meter. If we compare this to our total error budget, we can see that this long-wave spectral conversion is a small contributor to the error budget, where the goal is 0.5 watts per square meter, and the threshold is 2 watts per square meter. In the shortwave domain, we have 4 spectral channels, red, green, blue, and shortwave infrared, which is sensitive to surface spectral albedo and the cloud optical depth and cloud particle size. Again, from this, we can reconstruct the broadband radiation by a regression relation. And this time, the accuracy is 0.1, or the fidelity is 0.1 watts per square meter at the monthly mean level, which is a very small contributor to the error budget, where the goal is 0.25 watts per square meter, and the threshold is 1 watt per square meter. For the second problem of angular conversion, we will rely on the fact that the cameras have a wide field of view, and so when ECHO flies over a given scene on Earth, it observes this scene on Earth from different angles. The one angle which is important in the long-wave case is the viewing zenith angle. What you can see here on the left-hand side, with the right-hand scale, the red curve, shows you the uncertainty from which you can reconstruct the flux from a single radiance as a function of the viewing zenith angle. And you can see very clearly that there is a region where the sensitivity to the scene is minimum, and there, at 55 degrees viewing zenith angle, we have a sensitivity of only 0.8 watts per square meter, which is almost 1 order of magnitude lower than the 7.1 watts per square meter that we have near nadir, which are the classical viewing conditions. And so if we take a very simple baseline algorithm where we pick the best angle to do the radiance to flux conversion using only one angle, we already obtain a monthly mean uncertainty of the order of 0.15 watts per square meter, which is well below the requirement of 0.25 watts per meter. Within phase A, we will exploit the full multi-view capabilities of ECHO, so we will exploit all the angles, and we will further reduce this uncertainty. In the shortwave domain, the IDs are similar as in the long-wave domain, but things are more complicated, because in the shortwave domain, we don't only have one angle, but three angles which are important. So besides the viewing zenith angle, we have the relative azimuth angle and the solar zenith angle. But again, we can pick the angle with the lowest uncertainty. It's also important to realize that since we have these three angles, it's important how ECHO flies over a certain scene. So what you see here on the left-hand side is a case, the black line shows you a case where ECHO passes almost through the zenith for a given scene on Earth, which is the best condition. In this case, we have not less than 8 points observation points with an uncertainty below 1 watt per square meter. In the general case, average over all overpasses, at the instantaneous level, we estimate an uncertainty of 1.2 watts per square meter. And if we convert this to a monthly mean estimate, it's 0.2 watts per square meter, which is below the requirement of 0.25 watts per square meter. Again, we will further improve upon this during phase A, exploiting all the angles. And we are quite fortunate that we can develop a new algorithm with freshly available 3MI data on MATLAB second generation, which will be available during phase A. What you can see here is an illustration of the ECHO forward model. So it's based on the well-known RT-TOF radiative transfer model, where we have developed special coefficients for the ECHO spectral channels. So what you've seen is animation illustration of both the spatial-temporal coverage of ECHO, as well as the rich spectral information content of ECHO, both in the shortwave and the long-wave domain. And then last but not least, a key point for ECHO is the cross-calibration of the cameras by the radiometer, and that we validate by participating to the Magic Avalon campaign, which took place last month, but with already a test flight in April of this year. So this is an airborne campaign. The instruments of interest for us are the OSIRIS instrument, which is a wide field of view narrowband camera. And we have developed a special baffled pyranometer, which is a wide field of view shortwave broadband radiometer with a field of view completely contained within the camera field of view. And what you see here on the x-axis is the measurements by the radiometer, and on the y-axis the reconstruction of the radiometer measurements based on the cameras. And you see that already in these very first results, we have very encouraging agreement between both, showing a good cross-calibration capability of the cameras by the radiometer. And with this, I hand over the word again to Jackie Russell, who will speak to you about the international context and synergies of the ECHO mission.
So we've heard we have a gap in our measurements. No current observations have the accuracy we need to directly measure the Earth energy imbalance. And our determinations of it that we have come with a latency that is too long for our needs. ECHO is a unique instrument that fills that gap to directly deliver the Earth energy imbalance measurement. You've seen we have an innovative concept in order to achieve this. You have seen we have an engineering solution to achieve the accuracy that we need for this measurement. And you have seen the study showing the scientific feasibility to solve the 200-year-old search for a key climate indicator. We have long wanted to measure this, but the time to do it is now. It is increasingly urgent that we do it, and this is recognised by multiple international agencies. ECHO's observations lie at the heart of ESA's cross-cutting energy fluxes science theme. As stated in the ESA's Earth Observation Science Strategy, the need to quantify energy fluxes at global and regional scales, for example, by measuring the Earth energy imbalance, The Earth energy imbalance has been added as a new climate indicator by the World Meteorological Organization in their State of Climate report last year. They state, the Earth's energy imbalance combines information about changes in all parts of the climate system in a comprehensive and holistic way, allowing better quantification and prediction of changes in the climate system. The GWEX programme initiated an Earth energy imbalance assessment. As the GDAP EEI assessment panel state, measuring and understanding the Earth energy imbalance, its time variability and long-term trend is essential to understanding the current state of our planet and predicting its future evolution. ECHO's science goals align with the World Climate Research Programme's 4 pillars of their strategic plan. Our goals address fundamental understanding of the climate system. We will determine the pace of global warming. Prediction of the near-term evolution of the climate system. We want to understand ongoing trends. The long-term response of the climate system. Our goal to constrain projected warming. And we bridge climate science and society by providing timely, objective evidence to steer climate actions. ECHO goes beyond the current capability and fills an urgent gap. It responds to the GCOS implementation plan to explore new ways to improve estimates of Earth energy imbalance with novel remote sensing technologies. Our operational satellite missions dedicated to addressing the radiation balance are reducing, and none of them can directly measure the Earth energy imbalance. Going forward, we're at risk of having none that can significantly contribute to the problem at all without ECHO. ECHO imagers have downstream applications and interests with other users because they provide similar channels and resolution to the geo imagers. Their wide coverage and multi-angle observations may be of interest to test essential climate variable retrieval algorithms, produce supplementary products, or of interest for numerical weather forecasting, weather prediction. But more immediately, ECHO's primary products underpin the efforts of multiple other missions. Missions dedicated to studying and understanding multiple processes within our atmosphere to improve our ability to model them and the radiative fluxes. ECHO underpins these efforts, providing an anchoring measurement of the top of the atmosphere, energy budget, and Earth energy imbalance. The ECHO mission will deliver game-changing benefits to key strategic activities that underpin international climate science, policy, and society, enabling high-level intergovernment coordination around climate actions, informing economic modelling, establishing objective evidence to monitor and steer climate actions, providing vital independent oversight of any solar radiation modification, underpinning research of how the water and energy cycles shape our world. If Benoit can join me. The Earth energy imbalance is the most pressing scientific challenge for the sustainable future of humanity.
If you make ECHO fly, you will put the climate science community in a position where we will be able to close the energy budget from the top of the atmosphere down to the bottom of the ocean at the level of a few tenths of watt per square meters. It never happened before. And that's a game changer for very simple, fundamental questions like how much our Earth is warming, why is it warming, how it is warming, and how much will it warm in the future.
And now we'd like to hand over to Isa to tell us about the programmatics. Thank you very much.
Good job. Well, I'm still standing here in front of a slide which I take no credit for, but I can already start. Again, this has been a fantastic and amazing presentation by the team. Again, we have seen, as for the presentations yesterday, how much hard work has been going into the studies, into the last 2 years of coming to these results, and then the final stretch with the reports and also preparing the presentations. I know how much work is going into this, and I would really like to thank everybody, the presenters, the teams, industry, everyone that has been working so hard to give us this fantastic last what is it, 85 minutes of presentation. Thank you very much again. And I'm still standing in front of the wrong slide, so so let me just go forward. Can I? Yeah, so. All right, so we're coming again to the more, say, mechanical bits, the more bookkeeping bits. And as you have seen already yesterday, I will make this very short. This is mainly on the scientific maturity. It's the programmatics that we are setting up also on the ESA side to ensure that also we can confirm that the maturity that we're expecting at this level has been reached. And as yesterday, I've gone once through it basically in the long run. I will also again make it a bit shorter also to give Bernardo a bit more time to go into the technical details. And at the end of the day, considering the ECO Phase 0 scientific preparatory activities, as they've been documented in the reports, and I really invite you to also look into the reports for mission assessment and today's presentation, the MAC, the campaign, and the study teams have really shown that the mission has been demonstrating what we call scientific mission concept feasibility and assembled all the required evidence to justify that they are at the scientific readiness level 4, which is our, say, programmatic assessment point for the science at this stage. So I come to the slightly more interesting bit. So regarding on the risk with respect to the scientific critical areas and risk, the EUCOMAC, the campaign teams, study teams, they consider that the mission is of low scientific risk based on the results using the established external data sets and the complementary observations that are being done or that have been provided, and also based on the established radiative transfer models and simulations. Of course, should the mission be selected, there is a roadmap which is going forward in order to go towards the higher SRL, towards SRL5. And this roadmap includes as key points the inclusion of realistic system and instrument characteristics to study, in particular, the error propagation and the discrimination of random and systematic errors. Then also, of course, to enhance the performance simulation, addressing the optimized data binning, solar intrusions, and control surfaces coupled to the orbit, and of course then also closure of the polar residual. Then further for the assessment of the sampling error for the mission objective 2, which is on global maps of long-wave and short-wave radiated fluxes. There it will be the tailoring of the scene identification and the radiance to flux conversion. And with this we can say that the Phase 0 objective to mature the mission science to proceed into Phase A has been achieved from our side. And with this, I hand over to Bernardo for the technical assessment. Thank you.
Thank you, Torsten. You don't see the monitor, but I have 22 minutes, so something must be wrong. So thanks, Torsten. Thank you. Good morning, everybody. As yesterday, I will introduce a summary of the technical part of the programmatics, starting with an overview of some outputs of the Phase 0. And as you've seen in the technical part during the Phase 0 preparatory activities, each consortium has defined a system concept with the capabilities to fulfill ECO mission objectives and requirements. As also yesterday, you've also seen that, or you will see now, that the Phase 0 has identified the main technical risks and also the critical items for the mission. And risk retirement activities have been initiated, as presented in the technical part, and a pre-development plan has been put forward in order to increase the TRL and retire the risk during the Phase B1 and to reach TRL 5. In terms of title is missing heritage. Apologies for that. Heritage, critical areas and risks. Also for people that might have not been yesterday, when we're talking about critical areas, we are talking about items that are at low TRL, but also areas that are crucial to fulfill the performance of the mission that might not necessarily be at low TRL, but nevertheless, it's very important to keep focus during the Phase A. Both plat and satellite level and system Both consortia base their platforms on the Copernicus Sentinel expansion mission heritage, with a reuse of the avionics, with specific mission adaptations, particularly on the EOCS software, in order to implement the geosteering, but also in order to take into account that both satellites are in stack configuration and they will need to deal with its deployment. All other major subsystems for both spacecraft require design which are driven by the mission needs, particularly because of the stack configuration, the non-synchronous orbit, and also, as you've seen in the system design, due to the coupling between the platform and the payload in the way they are mounted. None of these adaptations are considered to introduce significant technical risk at this stage. ECO fits within Vega mass and fairing envelopes with margin for potential design evolutions. As you've seen also in the technical presentation, Concept B has more margins with respect to Concept A. At payload level, the Sun radiometer is building on flight heritage instruments, data, for instance, which is also using the same electrical substitution principle that Luca has described in the technical part. And in this particular case, for the Sun radiometer, direct heritage on the instruments can be applied, and it is not appreciated any critical areas of risk with this instrument. For the radiometer, it also builds on the same flight-proven electric substitution principle, and there are heritage on wide field radiometers. However, for ECO required performance, which, as you see, it is very stringent, the reuse at instrument level is not possible. Therefore, at critical items for the radiometer, the cavity and the thermal regulation system, in particular, the shutter electronics and coatings are identified as critical elements. For the thermal infrared, the visible and the SWIR instruments, of course, there is a lot of heritage on this type of instruments, but there is no direct instrument level heritage due to the wide field of view. In order to tackle the critical areas, pre-development plan has been put through with focusing on each of the instruments and particularly on the radiometer, in the manufacturing and test of breadboards and engineering models of the cavity and its control electronics to validate the feasibility of the closed-loop control temperature algorithms for its performance. In terms of the infrared instrument, pre-development's focus on detector adaptation, spectral filtering, the shutter design that you've seen, there is a shutter, and also in general to de-risk the detection chain in order to prove as well the radiometric performance. Also, it is proposed to have an elegant breadboard for the performance verification as well, also in representative environment. For the visible and the SWIR instrument, Consortium B is proposing pre-developments, a focus on as well verification of the performance, and also on demonstration on retirement of risk on the diffuser and the optical assembly for both instruments. And second priority for the radiometer, shutter and cavity coatings. Overall, the phase A, there is the pre-development plan proposed during the phase 0 is considered suitable in order to retard the risk identified and increase the TRL at the end of phase B1 to 5. In terms of the development approach, ECO, same as the mission that we saw yesterday, will follow a phase B2 CDE1 standard development plan, and the development of the instrument platform and satellite will follow a parallel route. For platform and satellite level, the instruments are qualified and developed independently, as we'll explain, and then they are delivered directly to the prime for system integration. Also, as you see, it is quite coupled, the instrument and the platform. At satellite level, Consortium B will follow a structural and thermal model, and while Consortium A, a structural model for the upper satellite, following by a proto-flight model, proto-flight model for the first satellite, flight model for the second satellite, right? Because remember, we need to multiply by 2 all the instruments and satellites. At payload level, the Earth and the Sun radiometers will follow it's proposed to follow STM, EM, QM, followed by a PFM for the first satellite and a second and a flight model for the second satellite. And simplification of the model's philosophy for the sun radiometer may be possible with not necessarily inducing risk due to the maturity of the sun radiometer. For the infrared, 1 EQM, 1 PFM, and 5 flight models for the first satellite, and 6 flight models for the second satellite. And for the SWIR and the VIR consortium, and the visible, consortium is proposing an EQM, a PFM for the first instrument of the first satellite, and a flight model for the second, for all the second set of the instruments for the second satellite. Finally, the last 2 bits for the schedule. As the missions that we presented yesterday is also driven by the instrument development and taking into account the current assumptions for the Phase B1 initiation and the Phase B2, launching the 2036-37 timeframe is considered achievable. Same as yesterday, the other programmatic considerations, eco-technical baseline adheres to the ECSS standards applicable to the Earth Explorer program, is compliant with the applicable space debris regulation. As mentioned, I will implement control re-entry, and there are no known ITU regulatory issues identified at this stage. In summary, for ECO, no technical mission showstoppers has been identified during the Phase 0 for the mission candidate to proceed to Phase A. And with this, I would like to close this part, moving to, excuse me, this slide, in which we would like to thank you to all the people involved during this close to 2 years since the call was initiated. Similar amount of people as we mentioned yesterday, hundreds of people have been working across all the activities, and I would like to start thank you to the MAC members, also the scientists involved in the science studies, the industrial partners at system level and the end-to-end performance simulator campaigns, which have you seen there has been also some campaigns, and of course, as yesterday, to you for your attendance and here and remotely. And of course, I'm forgetting my ISA colleagues. And thanks. This concludes my presentation, and I give the floor to René for questions.
Well, thank you. Thank you to the team again for a very impressive presentation of a very, very relevant society issue right now and political issue. So we will, when they are on the chairs, we will start the audience question and comments. Okay, we have the first one on the back.
Thank you. Peter Schad from DLR. Thank you for this very, very interesting and this very, very interesting presentation. My question with respect to this ECO candidate is that we have currently a mission in preparation or in development forum, which measures the far outgoing radiation. So could you please comment on the complementarity of the ECO mission to Forum?
It's not working. Yeah, it's working. Okay. Okay. Question on process related and global mapping. Jackie, you're taking it? No? Yeah. No? Steven? Yeah.
Hello, I'm Steven de Witte from the Royal Observatory of Belgium. So ECO is measuring the broadband radiation, so including, of course, the long-wave broadband radiation, which includes the far infrared. ECO is a monitoring mission, so it's making global maps, while Forum is a process study, so it's measuring only at nadir, and it's measuring the spectrum of far infrared. So there's a resolved spectral information in the far infrared. So it's complementary, but not replacing echo.
Do you want to add something, Benoit? Yeah.
Also, I want to point out, so the idea of ECHO is really to have the global integral, the energy imbalance, to close the energy budget. And with this framework, on the science level, when we use ECHO or EarthCare, for example, or Forum, we can really look at different processes and know what is the effect in a global energy budget which is closed. So ECHO is really about giving the context, the energy context in which we can see how the processes will affect this energy budget.
Okay, next one. Jonathan?
Hi, yeah, Jonathan Bamber, University of Bristol, Technical University Munich and Accio. So you said it's a monitoring mission, and a couple of times you showed the relationship between EEI and GMST. And that relationship changes with time. There are feedbacks in the climate system, like water vapor, like clouds, which go both ways, but there are also feedbacks which go one way only. So there's chemical energy in the system that only goes one way. So for example, like tipping points, like Arctic permafrost, forest dieback, those kind of processes that affect EEI in a different way to GMST over different timescales. And you've got some, I don't know what the length of the mission is, but you're measuring over some time period. How do you unravel the kind of non-linear and constantly changing relationship between EEI and what you claimed were kind of policy-relevant impacts on GMST and mitigation?
Okay, so there are several legs. You want to talk about the energy variation over time, and if we continue on the policy, maybe we give to other IPCC co-leader also.
So, first of all, if there is a tipping point, that will and it affect. So that should affect the energy imbalance if you want it to be a tipping point, at least at global scale. And so we will detect it with just looking at EEI, and we will find some anomalies. So that would be a capacity, a bit like with the solar radiation management. That's a capacity that will detect something's happening. That's the first point. Second point, one of the aspects of tipping point is that they make EEI changes with very small amounts of energy, right? And so the relationship with surface temperature doesn't change that much. You have to wait the energy imbalance to change, and then that will affect the global surface temperature. But then the relationship, because it's very small amounts of energy, all the energy is in the ocean. Part of it is because we're closing the energy, you can still find the energy which is in the ocean mix layer in the atmosphere and deduce the global surface temperature. Now, the tipping point will drive EEI is an initial way out of it's usually anomalies, and then that will react on global surface temperature. So we will know beforehand that surface temperature will have to change faster than expected because of the tipping point. Does it answer your question?
Yeah, well, sort of.
Okay.
I mean, you also said that climate sensitivity is not fixed in time as well. Yeah, the other point, climate sensitivity is not fixed in time either. So these are all changing relationships, and you've got this narrow window. Yeah?
Well, Jochen Morzke from the Max Planck Institute for Meteorology. I think what I would suggest to rephrase it slightly, what's changing in time is climate feedback. Climate sensitivity is the long-term, is the equilibrium response to certain forcing. The feedback changes in time. That has to do with spatial patterns, that has to do with a lot of things. And so far, we have been unable to observe that response in the energy budget to things that are changing on the ground. With ECO, we would be able to monitor these fluxes and would be able to tell the difference between the time-varying feedback and the long-term equilibrium climate sensitivity, which of course depends on the long-term climate feedback. And by being able to see that difference, not from model simulations, but from the observation, to see that instantaneous climate feedback, we would really make a huge change in our understanding of what's going on.
Are you happy, Jonathan?
Can I ask
Yeah.
Given that the mic is so close, I can't resist. It's something. I mean, you mentioned it several times. I didn't quite understand what you mean. You say multiple times in the report and also in presentation, unequivocal radiometric anchoring to EEI. What do you mean by radiometric anchoring to EEI? I don't quite sort of get what the point is there.
Is your question about anchoring the flux maps from the imager mission objective 2 to the M01?
Yes.
All right. Jackie?
So we directly intercalibrate the outgoing fluxes with the total outgoing wide field of view measurement, which we use to derive the EEI. So we directly anchor those flux measurements to one of the components that we use to measure the EEI, and it itself is intercalibrated with the other component. Does that answer it? Thank you.
Okay. No, we have Helen first.
Yes, I would like to come back to the diurnal sampling, which justifies the 2 satellites. You show result of a study with numbers and impact on the EEI uncertainty. If I understand well, you use models to compute these estimates. How do you compute it?
Okay, so I think that's the ubiquity question, and maybe you want to elaborate on the thousands of years of data that you have used.
So we use cirrus scenery as input, so that's based on observations. We have also looked at models, but they were not adequate. They had, symmetries in the diurnal cycles which do not exist in the real world. And so that's a bigger challenge to use cirrus. Okay, and then if you want a model, it's a model of the instrument, what it would see from the point of view of the satellite, and that integrates the flux. So there's no model in terms of climate models.
Can you specify the data you use?
It's cirrus SYN data. So it's hourly 1 degree data from the cirrus team. Is that an answer to your
Marcus
question?
First.
Oh.
Yep. Just a moment. Yeah.
Does that answer fully? Because do you want to explain the thousands of years of orbit simulation that you've made with this hourly? Yeah.
So in the simulations we have done, we have chosen many, many different orbits, many more than I could show, and they have been simulated over the full cirrus period, which is more than 20 years. And in total, more than 1,000 years have been simulated. And then from each satellite, or from all of these different satellites, we can make different constellations. So we have also looked at many, many dozens of constellations. That's how we end up with that single number, and that's the worst case, I should say.
Okay. Are you done? Marcus?
Yeah, thanks for the fantastic presentation. That also answered many of my questions actually already. I still want to ask one question which I think is already clearer for me now, and that is on the 0.3 watts per square meter accuracy that you think you have demonstrated. My understanding is this is entirely theoretical at the moment. And is there any means to prove that independently with some experimental approach? That would, of course, be a very strong underpinning of that very critical requirement of your mission.
Right. So there are 2 legs to this answer, to this question. There is in the error budget that you have seen, there is a sampling error, which Thorsten can elaborate on, and there is the instrument part that relates to the relative radiometric accuracy between the Sun and the Earth radiometers.
That's what I meant.
Okay, that's not theoretical. And Luca, maybe you might be able to elaborate what we learned from TRUTH, the breadboard, and the risk retirement activities here.
So indeed, to retrieve the 0.3 watt per square meters relative accuracy between the two radiometers, so you have to do an error budget, a detailed error budget with more than 20 contributors and even more, maybe 35 if you detail all the electronics contributors. Excuse me, where is the...
The question came from here.
Oh, okay. Okay, thank you. And then, so you have the different contributors. You can say that you have the optical one. It includes the precision aperture, the diffraction, the stray light. You have the thermal one, the thermal environment, the optoelectrical inequivalence. That is one of the most important one. We even had a dedicated risk retirement activity specifically on that term because it was the largest contributor. And it was, in a few months, we reduced it by 1 order of magnitude based on the cavity geometry and the strategy for the thermal sensors and electrical heaters. It was optimized in that purpose. So the design cavity has been changed a lot from the beginning of the phase 0 to arrive at that. Then you can also separate each of these contributors into their temporal aspects. So you have the systematic effect, the bias, you have the temporal, but it's not only sufficient, we even added a third category to specifically monitor the scene-dependent effects, especially for the Earth, because at first we can start the simulation with a uniform scene, but this is not enough. You have to take into account all these inhomogeneities into the Earth scene that will have a contribute to this optoelectrical inequivalence specifically. And so when you do that, you do the error budget for each of the radiometer. And then this is the most important part, the relative residual difference error between these two radiometers is so you take all the ppm from each contributor, and when you have some similarities in the cavities from the solar and the Earth radiometers, then you can these errors will cancel to each other, not necessarily to 0, but they will reduce, and this gives you new values, new ppm values for this residual differential error. And when you have done your new error budget on that specific residual error, then we end up with a value that is depending on the Earth scene-dependent errors. I forgot the most optimistic case, but the 0.18 was the worst case. So the value is obtained between it was something like 11 or 12 and 0.18 watt per square meters. And here I only report the worst case, not an average case, only the worst case. And this is what we have obtained. This is at instrument level. This is why when Thorsten has shown you propagate through the surface, you have 0.23 watt per square meters.
Can I just clarify? Because you said this is not theoretical. So which elements of this assessment are really based on laboratory tests or whatever you have done there?
So I was mentioning the acquisition mode. Before we could have think that the shutter operation, the same as the solar radiometer, could have been used exactly the same as for the Earth radiometer. We have noticed that it was really complex to do that because of the thermal inertia. It was difficult to stabilize the temperature of the cavity with the Earth changing scene. And so we had another risk retirement activity on the acquisition mode with PMOD that based on the lessons learned for the Truth mission, they have developed in the past 3 years the continuous mode, the continuous acquisition mode. And with that, a newly developed algorithm, so an advanced algorithm that keeps track of with the information of the voltage and the temperature, and you keep track with the a priori values, and you continue to obtain the temperature difference between the two cavities, that is 0. So with this, they have developed the algorithm, and they have also developed the breadboard for the electronics, so it was measured in laboratory. And this is what I was mentioning when I was saying that it was not only theoretical. And now the next step for phase A would be to qualify that with a space environment to reach the higher TRLs.
Thanks.
Okay, we had the ESSC comment. No, it's you. Sorry. Yeah, that one. And then one stand after that.
Roberto Battistone for the ESSC. When you measure an imbalance, you need two terms. The Earth, which is complicated enough not to discuss it further, and the Sun, which is much simpler, but still over the 11 year of variation is of the order of 1.5 watts. So this is why you need to measure the sun. But my question is the following. You are measuring the sun only for an interval of time. And you talk about the delays which the Earth reply to change in the incoming flux, and delay due to various phenomena which are fairly complex. So the question is how you will become the most precise sun measuring device in the future, because in the difference the error counts. You must be measuring the solar constant very precisely, also in the variation of time. How you can separate this variation from other phenomena, volcanoes, changes in the global atmosphere performances. Imagine you mentioned intervention by humankind by changing the atmosphere structure to correct for the climate change. How you can gauge and correct for such an important variable, knowing that the delay of the reaction of this quantity are quite complex to establish.
Okay, so I heard in the first part of the question there was a question about the sun sampling error. Is that something you would like to hear, or do we go directly to the second part?
The question is about the accuracy you have in the sampling of the sun constant, and how these affect the actual imbalance tomorrow, in a month, in a year, the one we are going to measure.
Okay, the sun sampling error was not discussed here. It is in the report, but I'll give the microphone to Margit.
So on the sampling error, we have done a study based on the 30-year-long Virgo measurements on SOHO. And actually, we studied what would be the sampling error for the case that we only do 1 or 2. So in our study, we did only one. We took one measurement per day out of the 1 minute data set over the 30 years. And we came to the conclusions the solar sampling error is really a minor contribution to the whole Earth energy budget. It is actually only 0.005 watts per square meter. So it's really small, a small contributor to the Earth energy imbalance on the annual scale.
And then for the other leg of your question, maybe Johan, you want to complete? The EI?
Yeah, of course, as you said, the EI is a very complicated summary of a number of effects, but we have to compare what we plan here to the situation that we have today, which is where we have, for 20 years, we have no knowledge of what the actual EI is. And we will have that knowledge every year. So what we will be able to do, since we have the knowledge of surface temperature, which is fairly precise, we will have the knowledge on an annual basis of EI. We assume we will still be able, through detailed radiative modeling, to get good estimates of the radiative forcing. That means we will have all the components, and we will, of course, have, even though with some delay, what the ocean does. So we suddenly have that combination between what goes at the surface, what goes on at the top of the atmosphere. We will have that directly. So we can suddenly see how that radiative transfer in the atmosphere is working, how it relates from observation, how it relates surface temperature to top of the atmosphere radiation. And if we then combine that with what we have from the spatial flux measurements, we are able to go into the processes and look where things come from. But the crucial first step that no one would be able to do today is to link the surface temperature to the total radiation at the top of the atmosphere. Currently, we are blind there. So we begin with that, and then we break it down into the spatial contributions.
If I can, sorry, because I did not receive the question to my first question. Today, the solar constant, taking into account the variability it has over 11 years, has an uncertainty of the order of over 1 watt per square meter, okay? So this is a fact, this is a documented fact, okay? You can say that your sensor can measure it in absolute term, but will be the only one measuring that. So this has to be, in a sense, demonstrated, because the other one are unable to do so. So my question is, imagine that you find that the value, when you start in 36, whenever, there will be a given value, okay? This will influence the difference, because the outgoing radiation minus this given value give the imbalance. The question is how you can check that this measurement of the solar constant and the outgoing emission at that given time will really represent the imbalance without any delay? This is my question.
Maybe I can add briefly. So, of course, I mean, we know we have the sun varies at the 11th solar cycle, but also at smaller time scales. And the absolute total solar irradiance radiometers measure it to a precision of 0.5 watts per square meter. And for the incoming solar radiation that is reached at Earth, it's a factor of 4. So it's to a precision of 0.11 to 0.12 watts per square meter. So this is on the term of the precision of the measurement. Now,
So if I understand the question is related to, for instance, the CalVal. So how do we validate this EI number? So there is a first leg that we have heard of already, the calibration, all the pre-flight activities, the traceability to SI standards, etc., that we can do on ground. And then comes, of course, the validation of a number that you're the first to measure. So that's where you have internal self-consistency and verification.
So imagine we have an issue, whatever issue, and we are not measuring as we expected. The first measurement we will have is supposed to anchor the top of the atmosphere radiation budget estimate. Then we are in a position where we can test the closure of the energy budget. We have the planetary inventory, and we can just check that we are indeed closing the energy budget at a few tenths of watt per square meters. And if not, then we can look what's wrong. Because we have this global integral measurement, which is of unprecedented accuracy. It's very difficult to validate. But so we had the problem with sea level, Jonathan, do you remember? For many years, when we got JSON, we had unprecedented accuracy on the global integral, impossible to validate. But when we were able to close the sea level budget, then we could find whatever. If it's not closing, you can chase for the problems and solve for these problems. And this was a huge source of progress, because with time we could detect any problem. We are here in the same position now, because we're getting to this level. We will be able to, with the ocean heat uptake and the other terms, the ice sheet heat uptake and the other elements, from the first year on, we will be able to test the closure of the energy budget and see if we have something wrong, and then look for it.
Okay, Vincent Henry.
Vincent Ripeke, CMWF and HO. I have a question on the third mission objective, which is climate action. So I would like to give you a chance to elaborate a bit more on how the data from ECHO will be really actionable. Because in a sense, I don't think there is a dispute in the CEPSTA, in COP, about the fact that there is an imbalance. So it's good to measure, and it's good to close the loop of these 200-centric questions. Now, in the discussion at CEPSTA, how will this make a difference in a sense that I don't think it's something that is questioned by decision maker or stakeholder. The questions are more at the level of attribution. So how this information will unlock discussions of whether policies are really working, at what kind of scale these policies are working, how far this is a natural variability of the Earth imbalance or it's human-induced. Because I think the stakeholders are not looking at that from a science point of view. Your presentation was brilliant, but it's how this will bring something to the debate about the responsibility, the need for action, and that's where I'd like to hear a little bit more from you.
So bridging using the ECHO data to steer climate policies. We have a couple of IPCC lead authors here. I'm looking at who wants to answer, maybe Jochen? Yeah.
Yeah, I think I can take this up. The question is important. And 7 years ago, I published a paper which I started by a thought experiment. And I said, okay, let's assume the emissions reductions are put in place, like in the Paris Agreement. We are in year 2035, and we look back. Has the temperature increase slowed down? And if the answer is no, even you could imagine it may have increased, then my expectation is there would be a fierce political debate whether indeed the underlying assumption was correct. But what I also showed in that paper is that if you have a 30+% chance that temperatures would go up just from internal variability. And that was a topic we picked up in the sixth assessment report in my chapter 4. And what we have done, it's unpublished work, but we've looked at that, is if you could use Earth energy imbalance rather than the surface temperature gradient, you would get confident confirmation that emissions reductions lead to the desired change sooner than if you worked with a global temperature trend. And indeed, the statement there, it's based on one model, many simulations with one model. The statement there would be that you can tell the various scenarios apart with great confidence after only 15 years, which you would not be able to do if you use the temperature trend. And I am convinced that if there were unfortunate developments in the surface temperature trend, we would have a huge political debate at hand, but with EEI, we can quench that debate in the beginning.
Okay, we are open for the whole audience. Okay, Rosalia.
Ivana?
Okay, first of all, many thanks for the presentation. Were very well explained all the missions. I have a couple of questions. One is coming back to the diurnal cycle. If I understood well from your presentation, from the report, you are planning to have the diurnal cycle monitor 8 times over a year. We know that the diurnal cycle is not constant, depends on the quantity of aerosol inside the clouds. So how much you can explain how significant to have this information only for 8 times over a year? So this is my first question. The second question is related to what already was discussed. You obtained this unbalanced in 1 year, but we know that, for example, I'm an oceanographer, the ocean has long respond to so how we can use, when this data will be available, this information, together with all the information on the heat content of the ocean, to understand how the processes are balanced?
Okay, so the first question is about the statistical representativeness on annual scale to seasonal scale of the sampling that we're doing with 2 satellites. That goes to Torsten. And maybe you want to carry on with the second answer or pass the microphone to Benoit? To the second question, sorry.
Okay, so for the diurnal cycle, of course, we would like to sample it more than 8 times per year. But with 2 satellites, we can do 8 and get a good near global coverage in total. So the things that we can see and the variations that we see are both due to the orbit of the Earth around the Sun that changes the diurnal cycle, but it's also due to geophysical changes inside the system. And the main things that we can identify from the data, from the CIRRUS data, is, for example, the change of the surface albedo during spring and autumn, and the changes of clouds in the Southern Ocean are very evident, and we can resolve those changes, of course. But yeah, you're right. I mean, ideally, we would have the diurnal cycle every day. But with this setup, we can get 1.5 months sampling, full sampling of the diurnal cycle. So yes. Then to Benoit. Yeah.
Yes, so about this question about the ocean heat content and the Earth energy imbalance, and to which extent they are consistent. So first, I would say instantaneously, we will close the energy budget. So whatever energy comes in, it has to be in the planet somewhere. So by counting each bit of energy, including ice sheets, including sea ice, including land and ocean, we should find it back and close the energy budget. So I would say on each year we can check that. Now, you're right, the ocean has different timescales to respond to the forcing. And it's very important to look on longer timescales to see how much heat the ocean has taken up, because it tells you about the pace at which we are changing. Not the level. The level is really fixed by atmosphere and surface, right? And then the pace is fixed by the rate of the ocean heat content, the ocean uptake. To do so, what's interesting is that with just the first year of ECHO, but 5 years it's even better, but just with the first year of ECHO, we will anchor the top of the atmosphere radiation budget independently from ocean heat uptake. So then we have a new record that we can compare to ocean heat uptake. On at least 20 years, we have 20 years of CRS that we will anchor, but just with ECHO. And then since we have Argo 2004, we have about 20 years, so 25 years of CRS, 20 years of ocean heat content. Now we can start to see at which pace the heat is entering the ocean, and so constraining things like the vertical diffusion of heat into the ocean and the pace at which we have climate change. It answers your question?
Yeah. You got both answers, Rosalia?
Obviously, to have the budget at the top of the atmosphere is important. Not the issue is to understand, because you are saying that having this monitoring every year, you can observe and understand what is acting for policy, but you don't know what happens in the ocean. Perhaps is a memory of long-term time scale respect to the annual budget of that you monitor. So I think this is an important point to consider in order to understand how to use all this information. And then, obviously, we know very well that the computation of the total heat budget of the ocean has a huge error, because even if Argo provide us a lot of information, we have not sampling all the world of the ocean, and also the error are not small. Yeah.
Okay, thank you.
Yeah, I'm sure you remember year 2023, which showed this extreme spike in surface temperature, an increase by almost 0.3 degrees compared to year 2022. And some people were speculating, has the ocean started giving back energy to the atmosphere rather than taking it up? I must admit, when I heard that, I thought this is ridiculous. With a greenhouse effect as strong, the ocean must take up the energy. But then I looked again and realized we don't have the measurements accurate enough to exclude the possibility that the ocean gives up energy. And that was important for the public debate, because there was a scare. The ocean is radiating out and even amplifying and accelerating global warming. So from the current network with Argo, just for the reasons you say, the Argo network is incapable of saying what the rate of, whether the sign of ocean heat uptake from 1 year to the next. We have to integrate over a longer time. For 1 year, we cannot tell because of the limitations of the observing system. With ECO, we would be able to state unambiguously the sign of energy uptake of the system. And therefore, we would know, nothing strange, no unknown physics is happening. Okay, the ocean, we would still be limited for the same reason, but we would be able to confidently say the climate system is still taking up energy. And then I would even say physical reason tells us the only place where it can go is in the ocean, even though we cannot unambiguously define it from ocean observations themselves. So that debate, has the ocean started giving back energy, again, could be quenched within a single year. There would be no question. And this unambiguous determination of the sign, I should stress, we would achieve with threshold, not with goal. We don't even need goal to get that sign. So within a single year, we would settle that debate.
Okay, I would like. We still have 5 minutes to go. I would actually like to ask a question, or two small questions myself. To take the difference between two large numbers is very, very challenging. We know that. And making the standard deviation of the difference is difficult, but getting the error of the standard deviation is really uncertain. I noted that you are looking for 0.7 watts as your threshold and the 0.3 as your goal or best wish, and you had the 0.39 on the final orbit simulations. Now let me go to the side of a small systematic error, and it's completely unrelated. That's on the GRACE mission. GRACE and GRACE follow-on give us a 24-year time series of gravity changes on the planet, especially the decay of the ice sheets. And when we take GRACE for Greenland, we get 250 gigaton per year, 150 in Antarctica, 130. But when we change from the Earth is round to Earth is ellipsoidal, we get more than 10 gigaton change. That's 1 order of magnitude more than the flattening of the Earth. So my first question to you is, in all your simulations, did you really take into account the Earth's flattening of 1 divided by 297? It has a big impact because your cone will have 16 kilometer. It will have a bigger radius. You will see more sun glimpse and you see more effects of the twilight. So that was the first question. The second question is really that you lag a little part of the world. When you have an 82-degree orbit in inclination, what about the poles? The poles have a yearly signal. It's white in the winter, and it's not completely white in the summer, in the northern hemisphere for sure. So these were the two questions, the flattening and the polar.
Right. So the first question relates to the control surface and the ability to master that. That would be for Torsten. The second relates to the sampling error of not having this, small fraction of the pole. This is also for Torsten.
So, can you hear me? Yeah. So for the first question, so up until now, we had a round Earth. The data is from a not round Earth, so that's a little bit in that direction. But for phase A, we plan to use the actual orbits and the actual control surface that will be observed from the constellation, including the solar intrusions and the varying size of the footprint over the orbit. And to your second question, the polar gaps. So with an 82-degree inclination, we are missing 1% of the Earth's surface, and you're totally right, there's a huge annual cycle in that. So what we will be doing with ECHO is we will try to fill in those gaps. It's a gap that exists out where the satellite is observing. So one way to fill it is with the cameras that will provide the flux map in over the polar region. So it is in the field of view of the cameras. And with that, we can then calculate what the flux out of the polar, missing polar cap is.
Yeah. Okay, thank you very much.
And I should include, so an error estimate of that is included in the budget that I showed you.
Yeah. Just for your information, the circular orbit is 60 kilometers higher over the poles than the equator, just so you know that it's not a small quantity.
We know that, yes. Thank you.
Okay, let's go back still. We still have time for one question, or maybe two short ones. Following the clock here, even we could do more. Yeah. One question by the chief judge here. Okay, one more.
Very short one. Of course, what you are doing is a very interesting, beautiful mission, no doubt about it. But because I mean, so such an accuracy, because to be relevant in societal consequence and scientific consequence, every detail is important. You have two satellites, and you explain why. Imagine that one of the two does not perform as perfectly as you wish, and the other one becomes dominant. Are you able to save part of the mission?
Well, I will start briefly. If an Earth Explorer is based on one platform and that one platform doesn't perform or fails, then the Earth Explorer is lost. In that case, we're lucky, we would still have a bit of something. Whether that bit of something would be at the level of the Earth Explorer, no. But still some science can be done, but not to that level. It's a bit similar as having an Earth Explorer on one platform. If that one is degraded, doesn't perform or fails, then then we're doomed. I think we should stop here. Yeah.
But you don't have a number.
Well, the sampling errors were calculated. Well, maybe you can recall the gradients of the regional sampling error as an example.
Yeah, so of course for the Earth sampling we have always simulated one satellite at a time and evaluated its performance and so on. So I showed you some of the results. You get large continental scale errors. Of course, part of that we can find ways to compensate for, making assumptions. Now, the idea of ECHO is to not make many assumptions. It's to get to the truth, right? So that's what we would want to avoid. Of course, we would work with one satellite if we only have one, but we really need two to achieve the goals that we are trying to achieve.
Thank you.
Okay, the clock is out, but if you have more questions, we have this session in the afternoon. So I'll thank the team and the audience for all the questions and so on. And I have one announcement, just a brief one, that from now on I will not chair these sessions because I have a conflict of interest for the next presentation on CryoRad. So, of course, in the chair we are very clear that we do not mix in satellites where we have vested interest. Yeah, and from Rune I should say, now it's lunchtime and we convene again at 1 o'clock. Yep.